Hello guys, we're going to start our 18th lecture. In this lecture, I want to talk about periodic function and then we talk about Laplace transform of periodic function. So first we have to know what periodic function is. A periodic function is a function that repeats its values in regular intervals or periods t capital, and periods should be greater than 0. In fact, ft plus t capital is equal to ft. So for example, you know that a function like sine t is a periodic function. So if I plot sine t, here we have t. I want to plot ft equal to sine t. So you know that the plot of sine t is like this. It's periodic, it repeats itself, and it goes to infinity. So here it's pi, here it's 2 pi, here it's 3 pi, 4 pi, 5 pi, and so on. So you can see that the function starts from here and goes to 2 pi. After 2 pi, it starts again and it repeats itself. As a result, we can say that this period, which is equal to 2 pi, is period of this function. In fact, ft plus 2 pi is equal to ft, and period of function is equal to 2 pi. So we could find period of this periodic function. So you can do the same procedure for all the functions. For example, in this example, so you can see that the function starts from here, and then here is 1, after a is 0, after 2a again it repeats itself. As a result, the period is from here to here. Period here is equal to 2a. So period of function here is equal to 2a, because after 2a it repeats itself. Let's go to the next example. In this example, so you can see that the function repeats itself after b. So see here, 0 to b, we have a ramp function. After b, so it repeats itself. As a result, here period of function is equal to b. Let's go to other example. In this function, so you can see that we have a triangle. After 2, we have another triangle. It's the same. So the function repeats itself after 2. So as a result, we can say that period of function is equal to 2. The next example. In this example, we have sine t, but half sine. So the function starts from here, go to p. After p, it repeats itself. In fact, this range of time is period. So in fact, here it's t is equal to pi, because the function repeats itself after pi second. So now we know periodic function, and we know about the period of how we can find period of a function. As a result, we can go to Laplace transform of periodic function and find Laplace transform of periodic function using given formula. So if ft is a piecewise continuous on the range of 0 to infinity and its exponential order and periodic with the period of t capital, then Laplace transform of ft is equal to 1 over 1 minus e to the power of minus s times t capital, the integral from 0 to t capital, e to the power of minus t, ft dt. So in fact, the Laplace transform of periodic function can be obtained by integration over just one period, and it's really helpful. For example, let's assume we want to find Laplace transform of this given function. So if I want to use definition of Laplace transform, so we have ft, Laplace transform of ft is equal to the integral from 0 to infinity, e to the power of minus st, ft dt. So you have to find this integral. But you can see that from 0 to 1, we have one equation of this line. From 1 to 2, we have another equation. 2 to 3, we have another equation. 3 to 4, another equation. As a result, if you want to find this integral, so you have to find the integral from 0 to 1 of e to the power of minus st ft dt plus integral from 1 to 2 of e to the power of minus st ft dt plus integral of 2 to 3 plus and so on. So you cannot find this integral because it goes to infinity. So in this case, we have to use Laplace transform of periodic function, and we just look at one period. So in fact, Laplace transform of ft based on Laplace transform of periodic function, it's equal to 1 over 1 minus e to the power of minus s. So we know that t here, or period of function, is equal to 2. So as a result, we have s times 2. The integral from 0 to 2 e to the power of minus st ft dt. So now you can easily find this integral, and you can find Laplace transform of given graph. Now we solve one example to see how this equation works. So we want to find Laplace transform of the periodic function shown below. So if you look at this function, we have half sine, then it's 0. We have half sine, then it's 0. But the function repeats itself after 2 pi. So in fact, the period of function is equal to 2 pi. So we have to find Laplace transform of ft based on the formula that we had. Is 1 over 1 minus e to the power of minus st capital, the integral from 0 to t capital, e to the power of minus st ft dt. In one period, I can find ft. ft is equal to, just in one period, in one period. In one period, ft is equal to, when t is between 0 to pi, we have sine t, because this function is half wave rectification of sine t. And when t is between pi and 2 pi, it's equal to 0. It's in just one period. As a result, Laplace transform of ft is equal to 1 over 1 minus e to the power of minus t capital is 2 pi, so 2 pi s, the integral of 0 to 2 pi e to the power of minus st ft dt. It's equal to 1 over 1 minus e to the power of minus 2 pi s times. So the function has two equations. When t is between 0 to pi, we have sine t. As a result, we have to split range of integrals from 0 to pi plus from pi to 2 pi. So when we are in the range of 0 to pi, so we have e to the power of minus st. Ft is what? It's sine t. dt. When we are in the range of pi to 2 pi, we have e to the power of minus st. So when t is between 0 to 2, between pi and 2 pi, so ft is equal to 0 times 0 times dt. So this integral is equal to 0 because 0 times e to the power of minus st is equal to 0. As a result, Laplace transform of ft is equal to 1 over 1 minus e to the power of minus 2 pi s, the integral from 0 to pi, e to the power of minus st sine t dt. So if you find this integral, we can find Laplace transform of given function. So in the past we found the integral of e to the power of minus st times sine t times dt. In lecture 2 we talk about it. So that's why I'm not using integration by part here to solve it. You know the solution. I just write the final solution. If you know that, just note the integral of e to the power of minus st sine t dt. So in lecture 2 we talked about it. So it's equal to minus 1 over s squared plus 1 e to the power of minus st times cosine t plus s times sine t. So we just use this integral to find Laplace transform of function. Laplace transform of ft is equal to 1 over 1 minus e to the power of minus 2 pi s the integral is minus 1 s squared plus 1 e to the power of minus st cosine t plus s sine t from 0 to pi. It's equal to I have to apply lower limit and upper limit. So in fact, Laplace transform of ft is equal to 1 over 1 minus e to the power of minus 2 pi s. If I apply upper limit pi, so we have, let me just factor minus 1 over s squared plus 1. Then I apply the lower limit and upper limit. So if I apply upper limit, we have e to the power of minus pi s times cosine pi is minus 1 times minus 1, and sine pi is equal to 0. So 1 is 0. Minus, I have to apply lower limit, so e to the power of 0 is 1, cosine 0 is 1. So minus 1, and sine 0 is 0. So if I just want to simplify it, so we have 1 over 1 minus e to the power of minus 2 pi s. So we have, I just factor, so we have 1 over s squared plus 1 times e to the power of minus pi s plus 1. So we could find Laplace transform of this function. I can simplify it more. So I can say it's equal to Laplace. As a result, Laplace transform of ft is equal to 1 over, so 1 minus e to the power of minus 2 pi s, I can write it in this form. 1 minus e to the power of minus pi s times 1 plus e to the power of minus pi s times 1 over s squared plus 1 times 1 plus e to the power of minus pi s. So you can cancel this guy with this guy. So we will have 1 over 1 minus e to the power of minus pi s times 1 over s squared plus 1.